Chapter 8.1, we're looking at matrices and systems of equations. Our goal for the chapter is to write matrices and determine their dimensions. We're going to perform elementary row operations. We're going to use matrices and Gaussian elimination to solve systems of linear equations. We're also going to use matrices and Gauss-Jordan elimination to solve systems of linear equations. So let's talk about matrices. So this is the definition of a matrix. If m and n are positive integers, then an m by n matrix is a rectangular array in which each entry aij of the matrix is a number. An m by n matrix has m rows and n columns. Okay, another thing to know about this is that, for example, if we say A23, so if we're looking at A23, this refers to the second row and the third column. Okay, so it's the Aij, so I refers to the row and J refers to the column. So we're going to look at this first example, just looking at the dimensions of matrices, so pretty quick. This is, the first one is just a 1 by 1. This one is a 1 by 4. This one is 2 rows by 2 columns. This is 3 rows by 2 columns, right? 3 rows, 1, 2, 3, 2 columns. And so try this last one. What do you think this is? Okay, hopefully you know that's a 2 by 3. So pretty quick, but just to know, how do you label it? When we talk about it, here's a 2 by 2, and then multiply to a, for example, a 1 by 4. Does that work? So this is what we looked at last chapter. Here's the system. Here's what's called an augmented matrix. And then so notice where the numbers are, right? It's just the coefficients, just the numbers. And notice that the dotted lines, it separates the coefficients of the linear system with the constant terms, right? This is just our constants here. So that's what we do with the dotted lines. And then this is just a coefficient matrix. So there is no vertical line here. Now it's important that when you form either the coefficient matrix or the augmented matrix, you want to begin by vertically aligning the variables in the equations and then using zeros for the coefficients of any missing variables. So for example here, we have 1, -4, 3, and 5. And then, so that's all our x's here, all our y's here, and all our z's here. And notice here there's a hole, so you put a 0 there. So important to do that. So we're just going to do a couple examples real quick, just writing an augmented matrix, and then describe what is the dimension of the augmented matrix. So here, I think just by taking a look at it, why don't you go ahead and try it. Now as a hint, what I would do is, especially if you know there's a lot of variables in here, that maybe label it at the top, x, y, z, and w, and then we know the last column is our constant. So go ahead and try it out. Try out A and B. Right, if you tried this out, now it could have gotten a little tricky, and maybe you even want to write this all out, lining everything up. So for example, what I mean is you could, if you needed to, you could do x plus 3y, and then minus w here, so you know there's a hole, and then you have -y plus 4z plus 2w equals -2, and so forth, just to kind of line them all up to help you out, but not necessary, but it is useful if you are having a hard time with this. Now looking at here, we have 4 rows for the first example, letter A, 1, 2, 3, 4, and then we have 5 columns, 1, 2, 3, 4, 5. So it's a 4 by 5. This one, that one was pretty fast, there's no holes there. Missing terms. So we have 3 rows by 4 columns. Now let's talk about elementary row operations. So this is very similar to what we did when we were solving systems the last chapter. Now just in order to notate it on the side, just so you kind of know what's happening, it's good to kind of keep track of it. So if you're interchanging 2 rows, what you're going to write is like row A and then with row B. So for example, if I were going to change positions here, row, like if you rewrote it, row A, row B, or row B, row A, sorry, like this. So just kind of how you would notate it, that's what the arrow means. Then if we're taking a look multiply a row by a non-zero constant. So that's just going to be some constant times row A, and then of course C is not 0. Okay, then if we're adding a multiple of a row to another row, then this is a constant times row A plus row B. And we've kind of done that before when we did our equation. So we did like -3 to equation 1 plus equation 4. Okay, so similar to that, but we can write it in this form as well. So here's just elementary row operations. So just notice what's happening here. Just kind of see. Interchange the first and second rows of the original matrix. So here's an example. So here's the original, and then you notate it on the new one. So whenever you change it, this is where you put it over here. So then in order, like what happened from here to here, is that this is now row 2 and that is now row 1. We're going to multiply the first row of the original matrix by a half. So here's the original, and then notice we rewrote the new one, and then we said, oh, this is how we got the new row, is by multiplying 1/2 to row 1. Add -2 times the first row of the original matrix to the third row. And so they did do that, and then they notated it here, and so this is the one that changed, right? The last row, and so that's where they wrote their change here. So now in here, I just want you to identify the elementary row operations performed to obtain the new row equivalent. So look at the original and look at the new row and see if you can figure out what did they do to change it. So looking at this, you notice that they changed row 2. Something happened to row 2. And so what they probably did is multiplied -3 to this equation and then added it to the next equation. So let's try it. -3, 0, -6, and then you add it and you get 0, 1, and 1. And there it is. There's our row. So they did -3 times row 1 plus row 2.